he's won several awards. He's won the NSF Career Award. He's won the JP Morgan Research Award, the Amazon Research Award. He's written some seminal papers in this area. And on a personal note, Joydeep and I know each other way back when we were both undergrads in India, and we would compete in the same robotics competition, which is where both of our interest in robotics stems from. His team always won, but who's counting? So please join me in welcoming Joydeep to University of Maryland.
Thanks, Pratap, for the wonderful introduction. And it's always fun participating in robotics competition. So it's for anyone looking to get hooked, get bitten by the bug. That's an easy way of doing that. But today I'm going to be talking about things other than robot competitions. I want to be talking about how can we deploy autonomous service mobile robots, and in particular, keep them autonomous, right? So I want to build up to like what are the challenges and what are we trying to do to fix them. But I want to talk about like what are we after? So what is the vision? And I want to talk about it in 3 parts. First of which is what are the kinds of users do we care about, and what are the kinds of tasks that we're looking at, right? So an example of that is that maybe a groundskeeper on a campus like University of Maryland might want to ask the robot, hey, can you go around the campus and find which trees and shrubs need to be trimmed, and then come back and report to me, right? Or anybody might want at some point to ask the robot, hey, can you please get me some aspirin, right? Or the busy researcher wanting to ask, hey, which talk on campus has free food, right? And the important thing to note about these deploys and these tasks is that you should not require a PhD in robotics to deploy robots, right? And not even a bachelor's degree should be required for deploying robots. And in fact, the second thing to note about these kinds of tasks that I mentioned is that mobility is crucial and is going to be a core recurring theme of everything I'm going to talk about, right? So part 2, what are the kinds of robots I'm talking about? So I'm talking about things like ready-built robots or robots assembled from parts. The main things to keep in mind is that these are affordable and they're going to have limited compute and sensing. You can't assume that you'll have the best possible sensors or like a very large amount of compute, right? And we want them to be general purpose and customizable. So what are the environments that we want to deploy them in? We want to deploy them in places like campuses and commercial establishments and homes. And the things to note about this is that these are real human environments. You can't necessarily engineer them just for the robot to work well, right? The humans are going to occupy these places. And because of this, since there's inevitable like changes, there's going to be unanticipated characteristics with variations with location and time, okay? And putting everything together, the vision essentially is to have, this is a vision which I share with many of you here, which is to have autonomous service mobile robots deployed by non-technical users in arbitrary human environments, performing tasks accurately and robustly over extended periods of time, right? And just to whet your appetite about like what's the kinds of robots that we work with things like the Cobot, which is a custom indoor service mobile robot. It's an omnidirectional robot. The Jackal, which I'm sure you guys have quite a few of actually. This is a fun video because we put our Jackal to task to haul packages between the CS building and the robotics building, and also quadruped robots like the Spot. And what's interesting is that we're working on perception, planning, and mobility algorithms in general, which can be deployed on all of these different types of platforms, okay? And they're operating in the real world. So why is this a hard problem? Well, first of all, as you can imagine, this requires concerted advances across many subdomains. You can't just improve one aspect of it and expect things to work well together, right? You have to work on many things to get everything to work well together. Secondly, edge cases are inevitable. So if you think about some unusual scenario and you think that, oh, let's just assume that this won't happen. If you deploy robots over enough number of times, it will happen, right? And there will always be something new environments, new tasks, new ways to fail, which I'm going to talk a little bit about, right? So there's many challenges to long-term autonomy, and I want to talk a little bit about some of the insights that we have to address 3 sub-problems over here. So robustness to environmental factors, anticipating and overcoming failures, and adapting to user needs, okay? So let me talk about these robustness to environmental variations. So what do I mean by that? If you look at the videos that I shared, right, what's happening is that indoors, there are all these tables and chairs and these humans. Was the robot told where these tables and chairs would be and where these humans would be? No. In fact, what did the robot know when it was deployed in the space? Almost nothing. It knew where the walls would be, and that's it. Okay. Similarly, if you look at this scenario, the spot is navigating by a construction zone. We had no maps of the construction zone. The robot needs to deal with it on the fly, and similarly down here, right? This is also interesting because we weren't expecting to see cars on Speedway, which is technically supposed to be a pedestrian-only zone, but the robot has to deal with things like this. And the context of these changes that I want to first talk about is the problem of localization, which is you know that you have to take a left turn soon to get to the CS building. The question is this path now that you see in front of you the one that you have to take a left, or is it you need to go further and take a left later? If you're lost, if you're not sure what which turn you have to make, then you might get lost, or you might take a longer way to get to the destination. So what are some of the canonical approaches to solve this problem? You might think, hey, why don't we just ignore everything unexpected and only make sense of what you expect and reason about that, right? So this turns out to be not quite so good, because let's say you have a robot which has some maximum range and you have a bunch of observations and a static map. In the most challenging environments, very few of your observations are going to match the map, okay? All right, what if you instead decide we'll just remap things when things change, right? But if you go back to these scenarios, you find that there's changes which are constant. Like everything's going to change all the time. Your expectation that you'll be able to deploy robots often and frequently and everywhere enough to remap everything is not going to necessarily pan out. So what can you do, right? So what you can do is that let's look at the observations from a particular time step t0. Let's look at the observations at a subsequent time step t1. And let's start correlating the two of them, right? If you notice the correlations based on odometry, right, you get to see some patterns emerge, right? So first of all, you have these things which we call long-term features, which are observations which we expected to match the map, and they do in fact match the map. There are these things which it didn't expect to see, but it's consistently seeing them statically over the short term, and we call them short-term features. And there are things which it didn't expect to see, right? And they're moving around, and those are dynamic features. So if you reason differently about them, right, the key idea of this algorithm, which was essentially part of my thesis, was you end up with this algorithm called episodic non-Markov localization by reasoning differently based on these different observations, long-term, short-term, or dynamic, right? And just to give you a nugget of like how this works, the way we do this is that let's say you have a dynamic Bayesian net for Markov localization, where essentially you're tracking the states x0 to xn of the robot. What's happening is that based on the structure of this graph, it's essentially saying that each observation Si, condition on the pose and the map, can be entirely explained. Now that's not actually true, right? When you're in an environment with changes, you can't explain everything just based on your map and your location, right? So we augment this graphical model to include these varying nodes and varying correlations. So when we have short-term features, dynamically we can infer like which are the time steps correlated based on the existence of these short-term features and so on, right? And then you end up with a nice factorization of the probabilistic formulation, right? And I'm cutting to the chase to the very end, where you end up with essentially you have the belief of the robot over x from 1 to n. And you have this interesting property where you have a bunch of product of Markovian terms for every time steps, okay? Which consists of the observations of the long-term features and the motion model. And now you have a bunch of non-Markov terms only for the unexpected observations. What's interesting about this is that if you deploy in an environment where all of your objects match the map, these non-Markov terms go away and you're left with only Markov localization. So this algorithm automatically reduces to Markov localization when everything can be explained. If none of your observations match the map, you have all of your observations fall into these non-Markov terms, and you essentially end up building up a local map on the fly to make sense of what's going on. So this algorithm is essentially spanning the gap automatically between just making sense of what you see and like building a map, right? And just to give you a sense of like what this looks like in deployment, so here's an environment. This was at CMU where you had these movable chairs, these sofas, right? And on different days, you can see then that they're in different locations. So the purple dots are these short-term features, and you can see the robot has like accurately reasoned about observations which match the wall, which are the long-term features and showed in orange, and these sofas in different locations, and it's using these together, right? And what happens is that these long-term features are providing global corrections, while these short-term features are providing relative corrections as the robot's moving around in the world. So this is actually how we deploy robots on the UT Austin campus, right? we don't actually give it highly detailed maps of the environment. The map that you see is like overlaid onto a satellite image, which it only includes things like the architectural features. And on the right, you see a visualization of a robot navigating between buildings. And on the fly, it's reasoning about which of its observations match the map, which of its are unexpected, which of them are short-term, and it's just dealing with this on the fly. Okay. So this is how we actually get around the problem of not having to maintain long-term or like up-to-date maps. Question?
How do you decide which ones are long-term?
So to build a long-term map, right, so you do need multiple trajectories passes through an environment where the first time you go see an entity, you might think that it's long-term. But the second time you see it, you correlate that to your past observation, and you find that, oh, I'm seeing something where which passes through a space which I had seen on observation, so it gets erased. So we have a paper on long-term vector mapping, which essentially builds up these kind of maps over multiple trajectories, right? Okay. But more recently, if we were to redo that paper today, we'd probably use things like semantic priors to help guide this search as well, right? Okay. Okay, which leads to some more recent work that we've been doing, which is you have these environments with these movable objects, but guess what? These movable objects are not purely random, right? They're not like located entirely randomly. If you look at a parking lot, people luckily don't park their cars just willy-nilly anywhere, right? They have like somewhat reasonable distributions of them. So the question is, can we somehow use these long-term distributions of these objects, right? And that is exactly what my PhD student Amanda and Taijing, a master student in my group, they're looking at. They're looking at how can we leverage these long-term probabilistic distributions of these semantically meaningful movable objects, right? And this is going to be a paper that we'll present at IROS this year. And so how does this work, right? So one way to think about this at a very high level is that you have some observation likelihood. What is the likelihood of making an observation of a short-term feature, condition, and the pose? And one thing you could do, a first take, is that you could marginalize out all possible poses of this object, right? And then you have the likelihood of an object being at pose O, right? So this might be a tempting thing, but it turns out this is not quite right because there isn't just one object. You don't know how many chairs are going to be there, right? So instead of saying that what is the likelihood of one object being at arbitrary poses, you need to flip this formulation instead around, right? And then you have to ask the likelihood of occupancy, right? What is the likelihood that a particular object of a particular class will be seen at a particular pose, right? So what's happening here is that we're marginalizing out over poses, but we're asking for a particular occupancy. So this CSCF equal to 1 implies occupancy at a particular pose. How likely is it that you'll make these observations, right? And now you have essentially a probabilistic object map, which is essentially this part of this formulation, which is saying, and how likely is it that I will see a chair at this location, or how likely is it that I will see a car at this location? So that's the formulation. Now it turns out that if you use this probabilistic distribution of movable objects, you don't need anything more. In fact, we've deployed our robot in like a parking lot over a week, right? And we've shown that you're actually accurately able to register these cars on parking spaces such that it actually is consistent with the satellite image, which was not used for this algorithm. And if you compare that to other algorithms which assume that the world is static, like Google Cartographer is an excellent algorithm if your environment is static, it breaks down when you build a map on day one and the next day things are completely different, right? So that's why the trajectories of the robot from multiple days are actually not consistent. Okay, so this is one way you can think about environmental variations. There are other ways in which you can have environmental variations, one of which is adapting to different types of terrain. So you deploy a robot on the campus, and there are all of these different types of terrains, like mud, grass, et cetera, et cetera. Why is this a problem? So when you're actually doing motion control on these robots, what you have is some desired trajectory coming from a navigation planner, and you're using a model predictive controller to essentially do something like an inverse kinodynamic control problem to find out what controls will affect this desired trajectory. But the problem is, to do this accurately, you need to take into account the world state, right? What does a world state include? It includes a lot of details about these types of terrains, but we don't even know how to represent this world state, and this world state is not directly observable to the robot, right? So this actually small niche problem led to this the side project, which with a bunch of collaborators, on high-speed off-road driving, including things like inverse kinodynamic learning just from inertial responses, from visual information, and how can you actually do nonlinear least squares optimization with them. Okay. So
also take into account terrain features. Terrain can be very crazy.
We do take into account terrain features from visual information, which I'll talk a little bit. Is that what you're talking about?
Yeah.
Yes, I'm going to talk about that. Okay. Or at least I'll give you a few insights about how we do this. Okay, so before we get into the visual information, the general formulation that we're going to say is that there is some hidden world state. We're not going to be able to infer this. But guess what? There is some unknown observation function which is giving us a sequence of observation. And conditioned on these observations, the terrain properties become observable to us, right? The simplest way to do this is to say, let's take the last 10 seconds of like your inertial measurements of a vehicle. And based on that, you should be able to predict what the kinodynamic response will be in the short-term future, as long as you're in the same type of terrain. But this model doesn't necessarily need to be done for different types of terrains. It's just conditioning based on this recent history. So this turns out to be quite effective. You can actually deploy this. We've deployed this on our scale 1/10 cars, and it's actually accurately able to track trajectories over terrains like these grass and leaves and so on, right? However, if you've been listening to what I said about like how we do this, where we condition on the recent future, a natural question is like, what about abrupt transitions, right? So here's a view of the viewpoint from the robot. This is a very nice video taken by Harish during his experiment. Here's a good place to stop. So the robot's currently on dirt, and now it's going to immediately go over cement very soon. So this recent history of observations are going to be quite inaccurate the moment it makes a transition, because the things that it's been on before is quite different from what it's seeing in the future. So how do you account for these things that are different coming up? Well, one thing you could do, of course, is to take into account visual input, right? And that's exactly what we did. So you have your camera view. We use the homography based on the geometry of the scenario to come up with a bird's eye view projection. And we extract patches based on the anticipated trajectory. And conditioned on this patch, you can actually learn a kinodynamic model. When we train this, what happens is that we drive the robot around, and the robot correlates the visual appearance of that patch with the inertial response of what it felt like when it drove over it, right? And that's how we train this model. And this turns out to be quite effective. If you use only historic IMU measurements, the robot spins out of control. Whereas if you use this visual model, it's actually able to accurately track the motion of this scale 1/5 truck on these different types of terrains. So this is a paper which Harish will actually be presenting at IROS, and we're quite excited about. Okay, so I want to talk next about anticipating and overcoming failures, but I can pause for a question or two if on anything that I've been talking about so far. Yes?
Have you incorporated like learning on the fly different terrain types, like trying to go over it you haven't seen before with your robot, identify how to deal with that?
Very good. That's ongoing research. Which is, I mean, we've done where you're new type of terrain, we've given some demonstration, and we go to pause and like run training. But yeah, you're talking about like during deployments, you're a new terrain, and how do you use all your past experiences to like correlate that to how do you anticipate things will happen? That's ongoing research, and I can talk offline about some ideas about how we're doing this. But yeah, good point. Yes.
The robots are very crazy junkers.
Yeah. We're all as roboticists, we always go around campus looking like, oh, this would be a fun place to run our robot. We're always on the lookout for that. So we have fun like identifying, oh, this is a place where there's like 5 different types of terrains. It'll be fun to run our robots here. Yeah, it's always fun. Yeah. There was a question back there. Nope. Okay. All right. Let me move ahead, and I can come back if there are more questions. So let me talk about anticipating and overcoming failures. Okay. So to set the context, why do we care about failures? Or in other words, what could possibly go wrong? Now, you're laughing. I mean, some people over here are laughing because, of course, you work with robots. Like, there's so many things that could go wrong. Okay, so let me just show you a video, but actually I'm going to pause this and ask you, all right, what do you think is going to happen here? So we have a jackal which is being deployed, and it's being sent to go to that building far off in the distance there. We have this scenario where there's been some construction work, and this manhole cover is covered with cones, and there's like landscaping at the same time, and there's like wet muck over there, and there's a cone there. What do you think will happen, and what would you have liked the robot to do in this scenario? All right, any guesses? Yes?
Go to the left.
Yeah, you want the robot to like go to the left, right? Just avoid this crazy situation and go to the left, right? What's actually going to happen? So let me just play this video. And this robot does this thing where it goes up to the cones. It doesn't hit it. It leaves like centimeters of clearance to the left, centimeters of clearance to the right, and it just went on. Now, this video keeps me up at night. The reason why it keeps me up at night is that most of the time we design our algorithms to take the best likely action, but we don't ever reason about what if I was wrong? What are the consequences of failure there? If you took into account the consequences of failure, maybe you shouldn't just take the best likely action here, but you should take a completely different thing, which as you mentioned, like go to the left, right? So this is the kind of problem that we're trying to get into, and just to set the stage of like the consequence of failure being high, we deployed our robots extensively, and like we came across a live fire drill training, right? So clearly bad things will happen if you make mistakes, okay? Okay, so we got to start somewhere. This is a very large open space. So we started looking at failures of perception, okay? So here's an example of a perception error. So we're using stereo vision, okay, to actually identify obstacles and like navigate down this hallway. Now, clearly there's nothing in this hallway if you want to just drive down this hallway, you just need a plan which will go straight. But this particular planner using vision comes up with this crazy idea of like going all the way to the right, you know, hugging the wall and then coming back to the middle of the corridor. Why? Why is it doing this crazy thing? This is the input image to this this vision-based planner. What's going on here?
Are you using a grid's top-down map and it's an artifact of that grid vision?
We're using grids, but it's not an artifact of the grids. But there's something in this image which is the reflection. All right, what is going on with the reflections? So this particular vision algorithm, stereo vision reconstruction algorithm, is making this assumption that the world doesn't have specular reflections. But guess what? The world does have specular reflections. And when it does, it thinks there's a hole in the ground, okay? Okay, at this point, you might, a knee-jerk reaction might be to say, let's just learn to identify reflections, we'll overcome these reflections, and we'll move on. But the problem, the deeper problem here is that no matter how good an algorithm you have certain assumptions. And when you deploy robots in the real world, these assumptions will be violated. And it's very hard to predict what these assumption violations are going to be. So to tackle this in a little bit more general manner, we came up with this algorithm, or this family of algorithms called Introspective Perception. And to put it simply, one way to think about it is that it's actually a higher order function. Introspective perception is a higher order function, which takes in a perception function that you care about and produces a new function that will predict when you get sensed inputs, which parts of your sensed inputs will be problematic for that perception algorithm. Okay, so this error prediction, of course, depends on which perception algorithm you're using. Okay. So how do you do this? I'm going to talk about two ways in which you can do this. One of which is actually readily available, which is called supervisory sensing. So you might have a robot with like your stereo cameras and a sensor like the Kinect, which is very nice, but only in specific environments. We don't trust it outdoors, but indoors, most of the time, it's actually really good, right? So now you can do this interesting thing where you do perception and planning using both these sensors, and you compare the plans. And when they agree, all's good. They're valid plans. When they disagree, you have divergent plans. But what's more interesting is that for this vision pipeline, you can ask it which patches in the image did you choose for coming out the plan. And when the plans diverge, you can penalize them and say, hey, there was something wrong in the image which led to your plan to diverge, right? And this allows you to actually automatically come up with like a data set of reliable, unreliable patches, which you can then use for training this introspective perception algorithm, which will, at deployment, then be used for competence-aware planning to predict what's the likelihood of making perceptual errors. So here's an example of like the output of introspective perception for the task of obstacle avoidance. This is the input image, and it's predicting things like perception, true positives, false positives, and so on. True positives are obstacles that there are in the world, and it is indeed detecting them. False positives are there are no obstacles, but it thinks that there's going to be an obstacle. And you can see that it's picking up these reflections, highlighting these reflections. Okay. We're also, of course, able to predict true negatives and false negatives. Okay. So what's more interesting is that this is implemented as a neural network. You can take the n-1th layer out of it and look at that as embeddings and cluster these embeddings in the representation space and look at how many clusters you have. And the clusters give you some notion of the different types of failures, right? So we discovered that this particular algorithm had 2 clusters of failures, and we sampled from them, and we realized like one class of these failures were reflections, which we knew about. And these other classes had these things like abrupt surface transitions. It turns out that human environments have these narrow textureless base bands around in our environments which don't have much texture, and there's an abrupt surface transition which is hard for predicting the depth accurately there. Okay, so this is one way in which you can learn to identify failures. Okay, I want to talk about some other ways in which you can have perceptual failures. Yes, Pratap.
So you mentioned that you take the outputs from like the 2 perception pipelines and then you compare the plans with each other.
Mm-hmm.
It's possible to have 2 plans that are not the same but are still valid plans.
Yes, we are very careful in like the setup that we do it, where we're doing things like in a local planning sense. And if you're only doing geometric planning, like if you're coming up with a plan which is longer than the shortest plan, then there has to be some reason or some difference. You're right, there are other scenarios where you could have both valid plans. We have not applied this in those kind of domains. I'm not I guess you'd have to think about like other properties that you'd have to apply there. Okay. Let me show you another way in which you can have perceptual failures. Okay, so this particular example of failure is, it's doing visual slam, which is essentially trying to come up with an estimate of how the robot's moving in the world, while simultaneously trying to come up with a sparse 3D reconstruction of the world. And in particular, what's happening is that you see these green dots. They're essentially interest points or feature points, right, on this image. And this algorithm is trying to come up with an understanding of where these points are in 3D in space while the robot is moving, right? So that's the simultaneous localization and mapping problem. Okay, so in this scenario, we have this input images, as you see over here. Something bad is going to happen. Something's going to go wrong for the localization and mapping. Can you guess what's going to go wrong? And can you guess why it's going to go wrong? There's something in this image which is going to cause failures. A shadow. Okay, all right. Indeed, it is a shadow that's going to be
very lighting along with shadows.
Okay, so the shadow is the cause of the problem. But any guesses as to what's going to go wrong? I'm going to play the video and see if you can guess it before you see the failure. All right. So at this point, this algorithm has picked out features on the shadow, which by all means is actually not a bad thing to do, because shadows have these very sharp corners and very sharp edges, which is exactly the kind of things features are supposed to pick up on, right? Yes?
They stay at the same place.
Yes, right. They stay in the same location in the image. And guess what? Since most of the features in your image are static in your image, your visual SLAM algorithm is fooled into thinking that the robot is static. Okay. All right. So this is another way in which you can have failures, right? So again, you could have written a shadow detector, but actually there's other things which lead to failures in these visual SLAM algorithms. Again, reflections, as I was talking to Dinesh earlier. And there's other things like lens flare and features picked up on movable objects like humans, which can lead to failures. So can we learn to somehow predict these sorts of failures, right? Okay, so I'm going to talk about how we do this. And to do that, I'm going to have to delve a little bit deeper into the mathematical formulation of how we do this, right? So the way we do this is that in Visual SLAM, in a very high-level view of what's going on, is that you're trying to come up with a belief over the camera poses x from 1 to t and all the feature landmarks 1 to L, right? Conditioned on your observed image features on your image plane, okay? And this is easiest thought of as like a product over all of time, over all of landmarks, the likelihood of observing an image feature conditioned on the landmark location and the robot pose, okay? So how do you do this? The way you do this is you say that your feature observations are drawn from a normal distribution with some mean and some variance, and this mean is basically just given from computational geometry. You just take your image, you take the landmark location, you project it onto the image plane using the projective geometry, and you say that there's going to be a Gaussian around that point that you're going to observe this feature from. This, of course, assumes Gaussian noise. And we've known for a while that these feature reprojections are actually not Gaussian, right? So I've just taken this figure from this really influential paper on bundle adjustment and modern synthesis, on which talks about how if you sample from a Gaussian, you end up with samples like shown in blue, which actually don't empirically look like the kind of distributions that we get, right? Okay, so the question is, you have some pipeline which is doing SLAM, right? We have this introspective function here, and we want to essentially use this introspective function to predict the distribution of these errors. We want to actually come up with the true distribution of errors, not just the Gaussian, okay? Okay, and if you could do that, then you can actually use that for different things. You could use that to predict where in the image to extract more interest point features from, where in the image to ignore features from, and also you could use this understanding of this noise distribution to come up with a context-aware noise model for the optimization, okay? So you have this post-hoc distribution of reprojection errors. How do we represent this distribution? And to represent this distribution, we take a page out of like robust visual SLAM, where essentially instead of just minimizing a least square, you minimize the least squares passed through a loss function rho. And what are the family of functions that you use for this loss function? One of the most common approaches is to use Hubel loss, where essentially you have a quadratic loss when you're close to 0. So when your features are well distributed, you give it a quadratic loss. When they're far away, you give them linear loss, okay? So what's going to happen is that we're going to learn to predict as a function of the image and the feature what the threshold should be, okay? So for each feature, we're going to be able to predict what should be the cutoff for going from quadratic to linear loss, okay? And that's essentially what we're doing. So we're taking these input images, we're using introspective perception to predict as a function of the image and where in the image you're looking, how much you trust these features, okay? So I'm skipping over a whole bunch of details about how we train this, but I'm just going to show you some of the results from actually deploying this. So in particular, introspective vision is actually able to predict like these features on the shadow are going to lead to errors. It reduces them. It's able to introduce features elsewhere, and for places where it's uncertain, it actually reduces the weight on them, and that allows the algorithm to keep tracking the robot's motion, right? And this is not with us explicitly telling it to look for shadows. it's done in an unsupervised learning manner. Okay, so we've actually done more quantitative analysis of this with both in real world and in simulation, and in particular, the main number to look for is the mean distance between failures, and what we show is that our algorithm is actually significantly able to increase the mean distance between failures both in the real world and in simulation. Okay, so this is how you would, some of the ways in which you can anticipate and overcome failures. And I can take like a question or two before I switch gears to talking about the next part, which is adapting to user needs.
So, you deal with all kind of uncertain environments. And based on your learning, robot takes some action. Do you even know it's a failure? Like, imagine I'm taking a path. I'm new to the campus. I think I'm going the right way. I always think I'm going the right way anyway, but I could be going the wrong way. How do I know I'm on the wrong path?
Okay, so Dinesh is touching on the question of what is right and wrong, but for robots. Okay.
Robot knows that it's wrong.
Okay, all right. Okay, so I think for there are some scenarios where that's actually a hard thing to codify, and that's actually part of what I'm going to talk about next. Sometimes it's hard for the robot automatically to understand it's doing something wrong. The human needs to tell it, you did something wrong, and then let me correct it, okay? But the kinds of scenarios where we've applied these autonomous algorithms is when there is some property, some geometric property, which is necessary for correctness. For visual SLAM, for example, you have the spatiotemporal consistency, right? Over time, if you're observing something static, the geometry should be consistent, right? So this is a property that we're looking for. The general insight is that you might not know what the correct solution is, but is there some property which is a necessary condition of being correct, okay? And that's the general idea, okay? But if you don't have that, then you got to take input from humans, and that's what I'm going to talk about next, okay? Okay, so let me talk about that, and I can take more questions about all of this later, okay? So one example of adapting to user needs is that you have a nice campus, like again, UMD is a very beautiful campus, and you want to tell the robot, don't just drive over the grass, like stick to the nice sidewalks, right? Okay, so given this problem, how would you actually tackle this? One tempting solution is to just do semantic segmentation on these images and then use that to actually to plan around in the world. There are certain problems with that, okay? So here are two input images, and here are the results of semantic segmentation. So the first problem that you see is that in some environments where there's clearly some grass there and there's clearly some dirt here, but in between there's like a continuous gradation, this discrete semantic segmentation comes up with an arbitrary boundary which is not capturing like this smooth continuousness, right? The second thing is that when you deploy this in the real world, you'll inevitably come up with things which are out of distribution for training of this semantic segmentation. And to overcome this, you need to give it more labeled training data to improve this, right? And collecting labeled training data is tedious and it's expensive, and you just don't want to do it, okay? So we came up with this algorithm called visual representation learning for preference-aware path planning. And the key idea is to leverage unlabeled human demonstrations to simultaneously learn visual embeddings of terrain as well as these preferences over these embeddings, okay? So what do I mean by that? So what's happening is that there are some input images of the robot at runtime. We use the geometric transformation to come up with a synthetic bird's eye view. When we're doing path planning, we're considering, like, say, going over this patch over here. We extract that patch and pass it through a learned visual representation function. And that gives you a terrain embedding of that terrain. And then you can pass it through a cost function to come up with what is the cost of going over that piece of terrain. So what is this visual representation function and what is this cost function? How do you learn those, okay? So as I said, we want to use unlabeled human demonstrations, and this is what they look like. So you ask the human to drive the robot from A to B, and here's a path, an example path that the human might take in this kind of environment, which makes sense. Except that the robot doesn't know about these types of terrains, and as far as the robot is concerned, this is the demonstration seen by it, right? This is actually quite useful to the robot, because then the robot can hypothesize, hey, there are these shortcuts that the human could have taken, but the human did not take these shortcuts for some reason, right? So now you can look at the synthetic bird's eye view and say that your visual embedding function of a patch on the path taken by the human and on the hypothesized shortcut must be dissimilar. We don't know why it's dissimilar. We don't know how it's dissimilar, but we know it's dissimilar, okay? Otherwise, if visually they were the same, assuming the humans making these choices visually, right, there wouldn't have been any reason to distinguish them. Secondly, let's say you have images from different time steps of the same location in the world. So for example, this green square is the same location in the world, just seen from different viewpoints in these two images. So the visual embedding of these patches must be the same. The difference between these, the visual embedding of this and this must go, the difference between them must go to 0. So combining all of this together, you can end up with, create a triplet loss for visual representation learning, which says essentially the representation difference between the anchor patch and the dissimilar patch must be greater than the distance between the anchor patch and the viewpoint invariant similar patch, plus a margin delta, okay? So this alone is enough, it turns out, to actually automatically learn terrain representation learning, visual representation learning for identifying different types of terrain, okay? And given that, if you've trained this fviz function, it's easy to learn this cost function JC. Essentially, all we say is that the human demonstration should be less than the hypothesized shortcut, okay? Okay, so we actually did a bunch of experiments with this, but I want to share one particular example where, let me just pause this and explain what's going on. We took the robot to a park. For a small section of this dirt trail in the park, we just joysticked a demonstration of this is what it means to follow this dirt path. And then we let the robot loose, and we just told it this, try to drive straight, but follow the path, right? Just stay on the path. This is in the input image. On the bottom right is the learned visual representation. It's false color. The different colors imply different representations. This is a cost map. The cost map includes black means low cost, white means high cost, right? So you can see that these, I'm going to pause it, for example, here. You can see it's able to pick out like the dirt path is visually different than the grass, and it's able to see that there's lower cost, and it is able to continue following this despite, it's not always a hard boundary between the grass and dirt, but the robot's able to cope with this and continue following this trail. Okay. Okay, any question about this? Yes.
So two questions. Why not learn the cost directly? Why sort of learn the intermediate representation and then learn the cost? The cost is the one that we actually use in the plan.
Yeah.
And the second question is, it makes sense that the visual representations for the patches show quite a bit of diversity. It's not clear to me why the loss also show that diversity. I would maybe have expected the loss to be almost binary. Sort of the navigable regions have a lower cost. Everything that's not navigable, it's not clear where the gradation for the non-navigable.
Okay. All right. Got it. Okay. So here's okay. So there's two questions. One question is why are we doing this in a two-step manner? First, learning the visual representation, then the cost. And the second is like, why does the cost function not have these abrupt transitions? So I'll address the first question first. The reason why we came up with this formulation is because we want to encode certain invariances to make the learning process easier. Encoding things like the viewpoint invariance and so on allows us to be a lot more generalizable than if you're just doing it end-to-end learning. I'm pretty sure like this end-to-end learning would work for the demonstrations. It wouldn't be able to generalize well, right? And we have some empirical evidence that that's actually true, right? Okay, so that's the answer to the first cost. The second question is the cost is actually a direct function mapping of the embeddings, and this is a continuous function. It's hard to actually enforce sharp transitions on them. Which is why we don't see them. And actually, if you look at the visual representations in these scenarios, in this scenario it's actually continuous. In scenarios where you have like a sharp transition, where there's clear cement and there's clear grass, you do see a very clear delineation in the cost. Okay. Any other questions before I move on? Nope. Okay, we can come back to this later. Okay, so I want to talk about some other ways of like adapting to user needs. So this is the kind of scenario where Dinesh was talking about, where the robot's doing something in the world and it's doing something wrong and it doesn't know that it's doing something wrong. And the human needs to tell it, you did something wrong. So an example of which is that if it's navigating around in the world and it doesn't have arms and it needs someone to open the door, you shouldn't go all the way up to the door and just block the door and wait for the human to open the door. So give some space to the human to open the door for you. Okay. That's one example, which we did explicitly encounter. Another example of these problems is these adaptable decision-making problems, like these social mini-games, where you've played these social mini-games. There's this thing where at the elevator, you have to stand somewhere outside and wait to enter. When is the correct time to enter? Should you wait? Should you go? Etc. Now, if you look at these problems, it's hard to specify these mathematical reward functions for these problems. You might not even know which mini games you're going to have in your new environment. And you can only get a few limited demonstrations. So it's actually very data parse. There's a lot of paucity of data in this scenario. So the insights, however, that we have is that a non-technical user can easily give a few examples. And in these kind of scenarios, examples that I've given, you can actually reason based on physically meaningful quantities. I'll talk about what I mean by physically meaningful a little bit. But at the high level, I mean, we've actually attacked this problem using a line of work called physics-informed program synthesis. And we've worked essentially with programmatic policies, and we've looked at how can we repair these programmatic policies, how can we synthesize them, and how can we iteratively improve upon them. This is work done by my PhD student, Jared, who graduated and is now at Bosch Research, and Simon, who was an undergrad, and collaborator Arjun from Northeastern University. And the key idea here is to use programmatic policies to perform these decision making. Okay, so what do I mean by programmatic policies? Okay, so what we're coming up with are policies pi, which map from state and previous action to the next action. Okay, the states are continuous, so you have things like Rn or like SE2 for like poses of entities. But these actions that we're dealing with are discrete low-level scales. We want to say that in this scenario, you should do like wait or follow or so on, right? So how do we do this? So in particular, we need a language for these robot action selection policies, and we want them to be expressive enough to be able to to be able to do these different tasks. But you want them to be constrained enough such that you can synthesize these policies, right? And here's an example programmatic policy. But if you look at these example programmatic policies, you can get a few insights. So first of all, there's some layered structure to them, right? So you can break this map into transitions between like these underlying low-level skills. The second thing that you can do is that the decision-making reasoning is based on physically meaningful things, like there's a relative distance between two locations. There's a relative velocity that's going over here, okay? Now, if you look at these, you can get some structure because you can't, for example, add a location to a velocity or subtract a location to a velocity. It doesn't make physical sense. So it constrains your space of what these symbolic programs should look like, right? And that essentially led to us understanding or thinking about these physics dimension-informed types in these languages to keep track of what is your exponent of length, time, and mass for every quantity. So for example, if you have a variable v1 which has exponent 1, 0, 0, it's of type length. Something which has exponent 1, minus 1, 0 is speed, and so on, right? But once you have these types, you can, for every operator that you have, you can annotate them with the constraints. For example, addition only makes sense for both the inputs to be of the same type and will produce the same type of the output, right? And in a nutshell, like this is the kind of reasoning that we do to search the space of programs to come up with symbolic programs, okay? And we essentially use enumerative search, and we use this layered DSL with that conditional structure that I've mentioned, okay? So how does this play out? So I want to show you some videos of how we give examples in this for demonstrations. So we have GUIs. For example, here's a setting for robot soccer, where we're in simulation we're teaching the robot, in this scenario you should use this low-level skill, right? And then we can play forward. Here's an example of social navigation where this blue box is a simulated robot, and these circles are supposed to be like humans, and where the humans like clicking on buttons to tell it like what underlying skill to choose, right? And given these demonstrations, the synthesizer is able to come up with these programmatic policies. Here's an example of like a synthesized policy for robot soccer, just executing in simulation. It's able to like quite successfully intercept the ball anywhere and score on a goal. For social navigation, it actually learns the behavior from the demonstration. So if you have demonstrations which are nice, it's actually a very socially compliant policy. Whereas if you give it demonstrations which are more aggressive, it does imbibe this property of being more aggressive in this environment. But what's interesting about these programmatic approaches is that they're extremely data efficient. In particular, LDIPs, which are our algorithm, reached, for example, 87% success rates with this particular policy, an attacker policy, and 81% success rate with a deflector, using only 750 time steps, which is about 10 to 15 minutes worth of demonstration data. If you use an LSTM to learn these same policies, they require many orders of magnitude more time steps for training. Okay? But there's another benefit to these symbolic policies. So let's say you train something in simulation and you try to run something in the real world. Of course, it doesn't work, right? So we trained this robot soccer attacker, and for some reason, it's not working. It's able to intercept the ball, but it's not scoring on the goal. But using these symbolic policies, we can give a few corrections and like correct these behaviors such that it suddenly actually just starts working, okay? Which is very hard to do with just purely neural modules, right? And we've also done that for the scenario of like this card operator door. Here's a before and after video in the real world where we added an additional state to a state the definition to this policy of keeping track of like doors. And then we gave it a demonstration that when the door is closed in your path, like give it some space until the door is open. So before the demonstration, the robot like goes up to the door. It doesn't hit it, but it just blocks the door from being open. Whereas on the right, it's learned that it waits for the door to be open for you before you continue. Okay, so this was a quick whirlwind overview of many of the things that we're looking at to overcome these challenges to long-term autonomy. And of course, there's like lots to be done, but these are topics for ongoing and future work. And I'm happy to take questions. If you want to see papers or videos or code about any of the things that I've spoken about, you'll find them on our website. If you want to use our code, feel free to shoot me an email and we can help you with that. You can also just browse them yourself as well. Okay? So I'm happy to take questions now.
Before we sort of do the questions, we have a token of appreciation from the Maryland Robotics Center.
Thank you so much. Yeah, thanks for hosting me. Thank you.
folks, questions? There's actually a question from the video stream
Okay.
that I'll read out. I don't know who the question is from, but I think this is about the first part of your talk. The question is, how do you train the robot running on different terrains, slippery and grassy terrains? We found it's really hard to train it in the real world, so we use Simulate to do that. But it seems like you directly train the model in the real world. How do you do?
Yeah, we train this directly in the real world, and when we are training it, we joystick the robot. So we essentially log what the commands are being sent to the wheels or to the motion controllers, and then what's actually the outcome. And then what we do is that we flip the question around and say, like, let's say the actual outcome is what you were trying to do. What you should have done is the control that here applied to it. So we flip it around to actually do this training. And that's actually the key insight. And when we're doing this, we don't allow the robot to be just autonomous. We just literally just joystick it around and you give it like a wide variety of types of motions. In principle, if you had a large enough space and you would safe from hitting obstacles, you could do this autonomously as well. Yeah. Okay, so that's how we do that. Okay. Yeah. Yes. Yeah.
We're talking about learning long-term features and short-term features.
Yep.
And short-term features are associated with the dynamics of the environment.
Yep.
And is there a limitation, like how fast or how slow those dynamics should change so that my algorithm will work, or like how does that relationship?
Yes, that's a great question, and this is an open research question. Like, how long-term is long-term for long-term and short-term? Eventually, you might think about that there is no such thing as long-term and short-term. Everything is short-term with a different time constant, right? But in our scenario, basically, if we see something that's temporarily inconsistent with an observation in another deployment, that's what we consider to be a short term, and then that's when we start looking at distributions for that. But so I agree in that in general we should not be thinking about like classes of them, but this is an open question. How do you do that for arbitrary time scales?